If you recall, yesterday we talked about the dot product, and we want to think about the dot product as multiplication, but at an angle. I want to think about the dot product as multiplication at an angle. We have two ways to define the dot product. The u dot v is the sum of the products of the corresponding components. That's the most useful way to calculate the dot product. The way we want to think about calculating the dot product is the magnitude of u times the magnitude of v times the cosine of theta, theta being the angle between u and v, and also between 0 and 180 degrees. So it's the short angle between u and v. That's the angle where we're multiplying at an angle. So we had some vectors yesterday. The vector u was 4i plus 3j. Use different ones. The vector v was 3i minus 4j. And the vector w was actually double v, because that's how we write it. And it was 6i. I think it was the other way around now that I'm writing it. Yeah, I've gone with this one now. So I picked these because the magnitudes were easy to pull, right? So the magnitude of u is equal to 5. The magnitude of v is also equal to 5. And the magnitude of w is equal to 10, because I'm using the same triangle. It's a larger version of it. What we notice is that when we calculated u dot v, if we calculate u dot v, I don't know the angle between these vectors, although secretly I know the angle between these two vectors. So we're going to calculate with the sum of the products of the corresponding components. So u dot v is 4 times 3 plus 3 times negative 4, and we get 0. And this tells us something about u and v. Some of you thought about this yesterday. So what does this tell us about the vectors u and v? The vectors u and v must be perpendicular. And we can see the perpendicularity in the slopes that I picked here. I picked slopes that were opposites and reciprocals. So what we're calculating here, if we think of our second definition of the dot product, is I took the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors. So if I get this product that's equal to 0, the magnitudes can't be 0. Those are both 5. And so the only thing that could be 0 is the cosine. So it must be the cosine of theta is equal to 0. And that means theta is 90 degrees. If we have a product that's equal to 0, then one of the factors must be equal to 0. So what we have found out is that U, the angle between U and V, must be 90 degrees. If we think about, when we think about multiplication at an angle, we think about how much of U is going in the same direction as V. And since they're perpendicular, none of it. None of U is going in the direction of V. We could think none of U is going in the direction of V. The component of U in the V direction is 0. And that's what the dot product is telling us. Now we also had the vector W, which was 6i minus 8j. Before I started, I'm like, well, you need to do it half scale. I'm like, well, nah, I'm just going to do full scale. And then W was like, oh, all right, we'll be using it. Never mind. So the way that we set the problem up is that W is in the same direction as V. When we calculate V dot W, I have 3 times 6 plus -4 times -8, which gives us 50. In this case, we have the magnitude of V times the magnitude of W, and we got all of it. We just multiplied all of it because V and W are going in the same direction. This is the magnitude of V times the magnitude of W times the cosine of the angle between them. Since the magnitude of V is 5 and the magnitude of W is 10, that means that the cosine of theta part must be equal to 1. It must be that the cosine of theta is equal to 1, and that means the angle between V and W is 0 degrees. V and W are going in the same direction. Because we're just finding the product of their magnitudes because they're going in the same direction. Since V and W are collinear or going in the same direction, and U is perpendicular to V, that means U is perpendicular to W. If we calculate U dot W, 4 times 6 is 24, plus 3 times -8, which is -24, and we're back to 0. Question? So we know cosine theta must equal 1 because the dot product is 50, and the magnitude of V is 5, the magnitude of W is 10. So 5 times 10 is already 50. Cosine of theta must be equal to 1. The only thing left for cosine of theta to be is 1. How's everybody? Okay? One of the other products, dot products that we had was negative v dot u. So the vector negative v will be negative 3i plus 4j. We'll just be going in exactly the opposite direction. So if I make dot product calculations with negative v and u, we should get 0 again, because if I just turn v around, that is still perpendicular to the vector u. So if I do negative v dot u, I get negative 3 times 4 plus 4 times 3. And that is still 0. That makes sense. If u is perpendicular to v, then u is perpendicular to negative v as well. That is not surprising. If we look at negative v dot w, so I got negative 3 times, let's get w back on the picture here. I get negative 3 times 6 is negative 18, and 4 times negative 8. We end up with negative 50. So negative v dot w is negative 50. Makes sense. If I took one factor out of each product and changed its sign, I'm going to change the factor of each, change the sign of each factor. That'll change the sign of the sum. But in this case, this is still the magnitude of v times the magnitude of w times the cosine of the angle between them. The magnitude, the magnitude of negative v. The magnitude of negative v is still 5, because it's a magnitude, it's not going to be negative. The magnitude of w is still 10, and so we can still figure out what the cosine of the angle between them is. Since 5 times 10 times the cosine of theta is equal to negative 50, that tells us that cosine of theta must equal negative 1, and so theta is 180 degrees. So there's the theta, there's the angle when we're multiplying at an angle. When things are in the same direction, the angle between the vectors is 0. Cosine of 0 is 1. And so we're getting 100% of the product of the magnitude. As soon as I start making an angle, we have cosine, think about cosine going through that first quadrant starting at 0. Cosine of 0 is 1. Cosine of 90 is 0. The amount of contribution to the vector as it moves away from the vector v. Here, cosine of theta is equal to, cosine of 0 is equal to 1. So we're just getting 100% of the product. Then as theta increases up to 90, we get less and less of the pen vector is going in the direction of the v vector. until we get to 90, where none of the pen vector is going in the direction of V vector. And so our dot product is 0. As theta moves into the second quadrant, goes past 90, cosine drops negative. So that negative cosine is telling us that the V components of the pen vector and the V vector are in opposite directions. That pen vector is now, we could think of working against the V vector. Makes sense because we're doing the cosine of theta. That's how much of one is in the other. And we now have a negative percentage. Until we get down to 180 degrees, where we're going in exactly the opposite direction. 100% of the magnitudes times -1. Any questions? How's everybody okay? So, dot product is multiplication at an angle. We're just trying to multiply the magnitudes. We're just trying to multiply the magnitudes, but the angle between them is going to limit how much one is contributing to the whole product. And we know that cosine is always between -1 and 1. So if everything's in the same direction, we get 100% of our magnitude product. Is everybody okay? That's the thinking that we want behind the dot product. There's how we calculate the dot product, and there's what we can use the dot product for, how we think about the dot product. We can use it to find the angle between a couple of vectors. There's another kind of vector multiplication where we multiply two vectors and come up with another vector. Mike Skywalker, just another one. But this one, we're going to stop at 2. We're not going to make more. Cross product, we only care about cross product in R3. Cross product is an R3 thing. Let's just think about the cross product as an R3 thing. Here's one of the things that we will want to use the cross product for. When we find the cross product of two vectors, we're going to get a vector that's perpendicular to both of those vectors. That's what we care about. U cross V, the cross product of these two vectors U and V, is going to be a third vector that is perpendicular to U and perpendicular to V. Pause for copying. Oh, I don't read that part of the teleprompter. So If you're wondering where the teleprompter is, I hallucinate the teleprompter on a daily basis.
Is that like a special ability to doctor?
Yes. Has nothing to do with all the hallucinogens I didn't take. I'm just kidding. Not taking any hallucinogens. I took them before work. I'm just kidding. Did not take any hallucinogens today. Today. I'm just kidding. I do not take hallucinogens. I do math. It's way better. So U cross V is a vector that's perpendicular to both U and V. Now let's imagine a scenario. I'm going to have to start drawing in 3 dimensions, but I've only got 2 dimensions that I can actually draw on. So we're going to have to use our imagination. So if I draw a vector V, and I have over here a vector U, imagine U coming directly out of the page. Everybody see the 3D plane or the plane that U and V are sitting in? They're like, oh yeah, the piece of paper that they're written on. And I go, no, it's not paper, it's plastic. This is a reusable notebook. Now you might notice that, so these 2 vectors, U and V, imagine a plane. Any 2 non-collinear vectors form a plane. They define a plane. So note, U and V are if U and V are non-collinear, then U and V define a plane. So I want U and V to be non-collinear. That means I want U and V to be linearly independent. So these 2 linearly independent vectors will define a plane in R3. U and V are linearly independent, so they define a plane in R3. So imagine a plane in R3. There's the vector U, there's the vector V. Now, when I say U cross V is going to be a vector perpendicular to U and V, you might notice that there are 2 vectors that are perpendicular to U and V, one going up and one going down. There's like a whole line that we could make perpendicular to that plane. So U cross V is going to be the vector according that's perpendicular to U and V according to the right-hand rule. What we're going to do, I drew them badly all the way around, is we take our right hand and we put our fingers in the direction of the first vector we list, U, and we curl them the short way towards V. And our thumb will point in the direction of U cross V. So U cross V will point, if I put my fingers in the direction of U and curl them the short way towards V, my thumb will point in the direction of U cross V. I forgot which one was up. Green will be up now. So U cross V will point this way. So U cross V will be perpendicular to U and perpendicular to V. We're using the right-hand rule. Fingers go towards the first one, you curl towards, curl the short way towards the second one. That means if we do V cross U, we take our right hand, I put my fingers in the direction of V, but I curl them the short way towards U. That's going to make the vector go in the opposite direction. It'll still be perpendicular to both U and V, but it'll go in the opposite direction. So that is an interesting thing. If we change the order in our cross products, we get the opposites the cross product is not commutative because if you change the order, you change the sign. That's weird. For a lot of people, this might be your first multiplication that is not commutative. Not your first non-commutative operation, but the first thing that we're calling multiplication, and it's not commutative. So we used the right-hand rule to determine the direction of the cross product. Here's why we might be interested in this. Notice that in three-dimensional space, we can define, actually, in one-dimensional space, but anyway, beside the point. In three-dimensional space, I can define a plane using two vectors that are in the plane. I can say this plane is the span of these two vectors. Take two vectors in the plane and say that's the span of it's the span of those two vectors. But this cross product gives us another way to define the plane using one vector. We can also define the plane by saying the plane is everything perpendicular to this one vector. We've got two ways to define a plane. Couple ways to define a plane in R3. I can say it's the span of two linearly independent vectors in the plane. This blue plane is a span of those two vectors. I could also define the plane by saying that it's everything perpendicular to a normal vector. I just stabbed the plane with a normal vector. So I can either define this plane as the span of these two vectors. If I just take these two vectors, whichever way they're going, that tells me what plane. Or I can grab one normal vector and say it's everything perpendicular to my normal vector. And that one normal vector, if I start moving it around, that moves the whole plane around. Any questions? Yes. R3 is three-dimensional space. Our collection of X, Y, and Z. It's like Cartesian coordinates have an X and a Y. Now we have X, a Y, and a Z. So it's three-dimensional space. The Cartesian coordinates where you have the X and the Y, that's R2, two-dimensional space. How's everybody okay? I didn't tell you how to calculate the cross product. If I had time, I would tell you how to do that. Actually, no, I wouldn't. It's Friday. Never do cross product calculations on a Friday. It's awful. It's more of a Monday thing. So that's going to do it for today. That's going to do it for this week. I will see y'all on Monday. Everybody have a good weekend. And thanks for playing. Have a good weekend.